not the routine, but we are going to do that. This is the last ITC lunch of the semester of the academic year, and shortly afterwards we will have a gathering at the ITC lounge. Or will it be here? It will be right here.
Yeah.
Okay, so it will be here after this luncheon. Everyone is invited. We call it Quito de Mayo because it coincides with the holiday that I think is tomorrow. At any event, we will present the Eric Quito Prize for the best PhD in theoretical astrophysics. Eric Quito is over there, and he endowed the prize. We are grateful for him for doing that. And it will be given to Flor Rockgarden about her thesis on gravitational waves paleontology. In addition, we'll summarize the year, the past academic year, and talk about various things that we plan for next year. So that will be after lunch. And at lunch we have 4 presentations today. The first by Dominika Krol from the CFA. She will tell us about the gravitational microlensing event in the optical light curve of an active galaxy with this phone number over there. And then we'll hear from Abby White, who is now listed as Harvard. She graduated from Wellesley. She spent the last year working on instrumentation in the Galileo project and was admitted to the astronomy department at Harvard starting next year. So we are really very happy to have her here. And she will tell us about what she has been doing over the past year. And then we'll hear from Adam Wheeler from OSU. Where is Adam? Over there. And he will tell us about Korg, a modern 1D LTE spectral synthesis package, which could be very useful to many of us. And finally, we'll hear about something that was all over the news. Well, unless you live in a cave, you haven't seen it. It's a star swallowing a planet. We know that these things may have happened, but actually it was observed, and that was reported in a paper in Nature yesterday, and all over the news. And Morgan MacLeod, who sort of led this paper together with Kishalei Deh. Where is Kishalei? Oh, here he is. Yeah, so Kishalei actually did led the observations, so he deserves the credit for discovering it. And then Morgan the credit for interpreting it. So we will hear from Morgan. A star swallows planet. That should be exciting and also frightening, I would say, because it will happen maybe to us, to the Earth, in, I don't know, 7 billion years, right? When the sun becomes a red giant. Don't lose any sleep, but it will happen. Okay, we'll start with Dominika Krol about gravitational microlensing. Please.
Thank you very much. So I'm a PhD student at Jagiellonian University, and I'm currently visiting CFA for a few months. And I would like to tell you about the project which recently was published, which is possible gravitational microlensing events in the Blazar S50716. But let me start with a brief introduction of a general idea behind gravitational lensing. So in astrophysics, we discuss it in 3 different regimes. Strong lensing, in which we can resolve multiple images of the source, and this is the regime in which we mostly talk about AGNs. Weak lensing, in which we see distortions of the shapes of the background galaxies behind galaxy clusters, and microlensing, the regime I want to focus on, in which we observe magnification of the light curve. So in general, microlensing is broadly used when it comes to galactic sources. So it allows us to detect sources which would normally be impossible to detect, like massive compact halo objects. And how it works is that whenever on the line of sight to the star which we observe, lens pass through, we observe this kind of magnification, which when we have a single lens, looks kind of like a bell-shaped. However, when we add another body, and recently exoplanets are being discovered in this one of the techniques of discovering exoplanets is exactly microlensing, because when we add another body to the lens system, we have distortion from this bell-shaped like magnification curve, and this is how we can detect this other body. But when it comes to exoplanets around the stars, the binary mass ratio in these systems is of course very, very small. And if we will move to the binaries with a bit closer masses, we will see that the magnification curves which we can produce are much different and much more complicated. So here I wanted to present you two magnification patterns for two different binaries. And 0.005, actually there is a typo here, and 0.1 mass ratios. And when we plot different source trajectories on those lens planes, you can see that we can obtain many different magnification curves which look in much more complicated way. However, I want to point out here, and I will go back later on to this point, there are certain lenses which, for wide ranges of the trajectories, produce kind of U-shaped dips in the light curves. So the question is if the gravitational lensing can be responsible for a part of AGN's variability. In general, we know that AGNs are very variable sources, especially blazars, on which I was focused on here, when the jet is directed towards the observer. And they are variable in all frequencies in many timescales. But maybe, and that was an idea proposed in the 90s, some part of achromatic variability of optical blazars can be due to lensing of the parts of the jet nodes, and we are talking here about hours timescales. But it is very difficult to find it, because first of all, since all of the event lasts around hours, we need light curves which will be very well probed. Secondly, the observation has to be long enough, because of course most of the observations of optical blazars are performed at the ground-based telescopes. It will be a problem to have a whole hour-long event and also some other parts of the observations. And what is even more important, we would need multi-filter data, because in general, as I mentioned, blazars are very, very variable sources. We need to, and the achromacity is one of the most distinguished features of lensing, gravitational lensing. So in order to at least have this kind of clue that this is actual lensing, we need to have achromatical events. So now I want to briefly talk about the history of microlensing in blazars, but in radio frequencies. So in 2017, there was a paper by Vadentham et al. In which they used the surveys which they performed in different frequencies in order, to try to find those kind of lensing events. And they came across a couple of candidates. Here I just show you the plot from their paper in which they present 24 years of the light curve of one of the sources. And they are claiming that those 4 U-shaped dips are actually due to microlensing events. So they believe that the macrolensing events in their light curves is caused by the binary, which would be depending on exact parameters, because in their case, they are not sure about the distance and exact geometry of the system, with the masses around 10 to the 3 to 10 to the power of 6 solar masses, which may be interpreted as some subhalo condensates or black holes within the galaxies. However, the question which I want to try to answer now is, can we find similar events in the optical blazar light curves? Those will be on completely different timescales. And there is one blazar which is very characteristical in the sense that the blazar S50716, if we want to say out loud this number, which is very variable also on the short time scales. So basically, whenever we observe it during the night, we will see some differences. And it made it a perfect subject for multiple monitoring programs. For instance, Whole Earth Blazar Telescope, which is consistent of a multiple optical observatories which are observing one object together, which allows us to have much longer observations. made multiple campaigns on the subject. Also, recently, we have test data. So in a sense, it is a perfect target because we have many filters, data from whole Earth laser telescope. They are reasonably good quality, and especially the DES data are perfect quality. So here I'm presenting you the Lightcurve from one of those campaigns published in 2016 by Bata et al. And as you can see, those are the data in different filters. And I want you to look at this part of the Lightcurve. So here we have a rise of the flux, the drop of the flux, plateau, and then symmetrical rise. This kind of behavior was actually found previously 10 years ago in the same object, as they point out in their paper. So in 2003 observations of whole Earth laser telescope, they found very similar dip, which consistent with this symmetrical rise and fall before and after minimum, which is plateau or at least symmetrical shape. And in those cases, they are achromatic. So we were looking for the similar events in different light curves of the source, and we found 6 other in the test data, which have exactly the same geometry. And we started to wonder, maybe all of those can be result of a gravitational lensing of the jet segments. So in our analysis, we're trying to fit those U-shaped dips with exactly binary lens model. And we managed to find one binary lens which could explain all of those variability events using only slightly different trajectories on the lens plane. So here you can see the events which we were fitting, data, and the fit of the lens. And the lens itself would have mass ratio of around 0.005, would be binary lens. And as you can see, we can obtain those kind of trajectories, those kind of magnification curves, which are required to produce those events for many different trajectories. So in a sense, we don't need a fine-tuning fitting of the exact trajectory. Then the question is, what can we actually tell about the lens itself? So there are a few constraints which we can put on it. First of all is the size of the emission region in blazars. We know that in general it cannot be smaller than the gravitational radius of the supermassive black hole. We know that our events last several hours, it's like 7 hours on average. So we know that orbital period in this binary has to be shorter than that because we need to have a stable length for during the event period. Then we have timescales of the events. So assuming something about apparent velocity of the nodes which are moving on the lens plane, we can say something about the parameters. And also we know that the lens has to be on the line of sight to the source for 20 years. And using all of that, we can say what would be the mass of the lens depending on the distance between lens to the source. So basically, we get upper limit from apparent velocities, we have lower limit from the time scales, and we can tell that our lens would have to be, of course, there is a huge uncertainty, and depending on where the lens would be located, it would have completely different masses. But we are seeing lenses from around 10 to the power of 3 to 10 to the power of 5, 6, depending on how far they are. So we don't know what it can be because, as I mentioned, it depends where it is. But the question is, can we actually expect this kind of sources? And there are some n-body simulations which are leading to this kind of binaries, and we expect that maybe they can be there. So let me just leave you with this summary slide. We fitted 8 events of the light curves changing in the blazar with one single binary lens. We estimated lens parameters, and depending on the source lens distance, they are pretty high range, but some of them, for a high range of the parameters, they would fall into these intermediate black hole mass ranges. And in order to find, in general, more of those kind of events, we would need an optical service which would observe in many filters and for a long time and with a good quality. Thank you.
Masses you are talking about are comparable to that of a globular cluster. So could it be a compact star cluster rather than point
Yes,
clouds?
that's also the possibility. So, but in general, so for instance, in the paper which I mentioned before, they mentioned that so it is possible to produce this kind of light curves both for the binary, but the binary can be also in like general, much halo-shaped mass. But in general, we need a binary there, which with comparable masses. Yeah.
And then the chance, the probability, you didn't talk about probability, but the chance
Yes.
of seeing something like that would be negligible.
Yes, that's
So
true.
how do you explain the fact that, you know, the probability for that is so small?
So the thing is that in general, I think it's difficult to say something about that because, as I mentioned, first of all, you need a lot of data, good quality data. So the only way to say if actually we have it would be to see it in many different sources.
Right.
And as I mentioned, this is kind of the only one which for now has enough of quality data. But yes, of course, that's one of the issues.
But in terms of the probability, it's the only one out of how many, if you were to estimate the probability?
Oh, but difficult for me to say, but this is one of the only blazars in optical ranges which has enough quality data. In the radio, they had survey of, to be honest, I don't want to give a wrong number here. I believe they found 4 or 5 this kind of candidates, as I showed you in this plot, and they had, I think, hundreds. I don't want to, I don't know.
Just a number to keep in mind.
I don't know.
The likelihood of lensing a quasar, not a laser, is less than 1%. It's a 10%.
Sorry, yeah.
So I guess there is magnification bias, which brings it maybe up to 1%, but not better. Go ahead, Matt.
Could you back up to the slide with the light curves? The one with the tests that go forward. Okay, so you see, there's all of this structure in the bottom of those, those light curves. Does that give you any information about?
No, because the thing is that also the source itself is variable. So in general, the biggest
That's
issue
variable.
here, yes, the main issue is first of all, if this is actually, of course, this, but also when you have the lensing, then of course there will be an imposed in-strict variability of the source. So not really. Yes.
Ramesh?
So normally when you have these double humps with a plateau, on the sides the intensity will fall off. Actually it will go below the plateau level.
Yes.
It didn't look like your light curves were doing that.
Yes. So in the picture which we have in mind, we are thinking that because in general all of this source is very variable, those kind of U-shapes are appearing in different states of blazars, like different variability. So we're thinking that in general, maybe in those moments, those are the moments in which general brightness of the jet goes down because of variability, and then we can see this lensed portion. But yes.
So you're saying the lenses you see preferentially when the source is dim.
Yes.
Why?
No, I'm saying that we say them in all of the variability, but in general, in order to see this segment which is going through, probably we would need in that moment. Yes.
Korean?
So if I understand right, you have 6 separate events. And
Yes, together with Web 8. Yeah.
And each one, so 8, and each one, here they're separated by a few days. And each one would be a different binary lens.
No, exactly the same. So the thing is that all of them can be produced by the same lens, exactly the same lens. But the thing is that we would think about it as a different segment being lensed basically in different periods of time, and we can produce it with one lens with different trajectories on the lens plane.
I see, thanks.
And the binary doesn't change much during this time to change the...
Yeah, that is one of our constraints, that we have to have binary, which is more like during the event time, it has to have stable, yes,
orientation.
exactly.
Was there another question here? Yeah, go ahead.
Yeah, are there any foreground or background sources like galaxies or whatever that you could confirm this lensing in?
For this one, no. So this one, we would have the lens inside, and those basically the distances which I showed on this plot would be distances more or less within the galaxy. So we would have to have it inside. Yes, there are no foreground or background sources in this.
So it's just 100 kiloparsecs, so it needs to be within the halo of the host.
Lots of stars in there.
it's not stars. This has to be massive, 10 to the 6 solar. It could be a globular cluster, as you mentioned. Anyway, thank you so much.
Thank you.
I meant as like backlight to confirm the lens with that. As like backlight to confirm the lens with that. Yeah.
Yeah. This one is a laser. It's very different.
All right, hi everyone. My name is Abby White. I'm a postbac research fellow here at Harvard. I've been working under Avi's supervision for the past year, and today I'm going to give you an insight on what I've been up to, which is instrumentation for the Galileo project. I'm going to start off just by talking about the project and its goals as a big picture kind of thing. We're going to dive into some instrumentation, so sorry for the theorists in the room. And then I'm going to touch on our data analysis approach, and then finally finish up with some of the things that I've been able to accomplish. So the Galileo project was co-founded by Avi Loeb and Frank Laukian in the summer of 2021, so almost 2 years ago, with a goal to bring the search for artifacts of ETC from accidental or anecdotal observations and legends to the mainstream of transparent, validated, and systematic scientific research. Within this goal, there's 2 branches of research. The first is unidentified aerial phenomena, or UAP. You might have heard the word UFO before. This is kind of a more generalized term for that. And to approach this, we are looking at artifacts within and near Earth's atmosphere. The other is interstellar objects, and not just any interstellar objects, but those that exhibit properties that are maybe strange in comparison to typical meteors or asteroids or comets. There's 2 relevant avenues of research within that. One is a rendezvous mission, which is in concept stages to an interstellar object. And then the other, which is well underway, is a fragment retrieval expedition, which I'm sure Avi would be happy to talk about. And today I'm going to focus on the branch that I work closely with, which is the UAP branch. And how do you approach a problem that doesn't have a history of, rich and validated scientific research? Well, here's our best shot at it. So here's our observatory system plan. So first we're starting off with the science traceability matrix. And this allows us to take well-sought parameters and connect them to observables or instrument requirements. We then feed this into an instrumentation design, which Alex Delacroix, who's sitting next to me, or was sitting next to me, very much helped out with. And then we kind of have 3 phases. So we're very much in phase 1 right now, on our way to phase 2. And this allows us to build a bunch of instruments that are, covering different modalities and are multispectral so that we can just throw everything at the wall and see what sticks, pretty much. Phase 2 is going to allow us to improve our AI algorithms, upgrade some of our sensors, and add some new ones to our instrumentation suite. The third operation is base of operations, which I'm really excited about. I guess one day in the future that'll be copies of systems all running beautifully and collecting data. I just want to point out there's also efforts at Wellesley College with a team called Celeste going on. They're working on a portable, non-weatherized observatory system and a mesh instrumentation system that are each an order of magnitude less expensive than the one we're working on. After we collect tons of data for a long period of time, then we'll go ahead and hit it with our theoretical analysis, as well as interpretation and modeling, and this will turn into some scientific peer-reviewed publications. All right, so for the instrumentation part, this is our phase 1 observatory system. You may have seen some of these components on the roof last summer if you were around. I'm going to buzz through each of these, so I'm going to move pretty fast, just as a warning. All right, first we're going to start off with our infrared wide field of view. This is our Dalek instrument. You'll see here, there are 7 infrared cameras around the base, and these are each 50-degree field of view looking in the infrared, and anything that they don't cover, the zenith boson up top is going to cover that 95-degree field of view. The blue things are just sunshades that prevent the detectors from getting saturated or damaged from sun, and on the other side it's wipers to clean the germanium windows that are there. We also have a near-infrared camera that's 180-degree field of view up top just to cover our bases there. We also have optical wide field, which is our Alcor instrument. This is a 180-degree field of view and is basically serving as our human eyes sitting there looking at the sky. We can take short exposures like 32 microseconds up to long exposures like 1 hour. This sits next to the Dalek, as you can see on the sketch down there. We also have optical narrow field with our pan tilt zoom or PTZ camera. This is a Beacon 8.0 security camera actually that we're using. And it has 4K resolution, so this allows us to see an object a lot in higher resolution than our other cameras, and it has 40 times optical zoom. The other cameras communicate with this one so that if we, in applying our algorithms to the data we're collecting with our optical and infrared cameras, there's something that's worth looking at, it will point this camera to go and zoom in and get a higher resolution picture of it. We also have acoustics, which is the Amos instrument. This covers 0.05 hertz to 190 kilohertz, covering both the infrasound, audible, and ultrasound ranges. It's important that we're getting this entire range because there are things that would be in that environment that might have signals in each range. So we have a wind turbine in the infrasonic range, an airplane in the audible range, and a bat in the ultrasound. We also have a passive radar system called Skywatch. This is in development, but this graph or image kind of gives you an idea of how it works. So it's passive, it's not emitting anything. And there's receivers that are spaced out, and they use FM radio signals with direct references coming straight from the transmitter and remote references coming from those signals bouncing off of objects like aircraft, and that'll help us localize them. We also have radio spectrometry. This is our Spectral instrument. This is using a signal hound spectrum analyzer sensor that goes from 9 kilohertz to 6 gigahertz. Our antenna limits this range a little bit, but it's an omnidirectional antenna, so it gets things in all directions. We also have a vector magnetometer. This is our Barnington magnetometer. Its range is plus or minus 100 microtesla. This is a kind of graphic of what the deployment will look like, a cartoon. It'll be buried 3 feet underground. That's limited by our cable length there, and that is just to ensure that there is not a lot of temperature variation going on. We're going to conduct the calibration of this to see how temperature might affect our readings of the magnetic field, so stay tuned for those results. We also have an environmental sensor. It's really important that we have a great understanding of what our environment looks like before we start making claims or doing any analysis here. So this comes with a bunch of toys. We got a particle counter, another magnetometer, temperature, humidity, and pressure sensors, other things like anemometers, IMUs, GPS, and all that jazz. All right, next we have ADS-B. These are signals that are broadcasted by aircraft. You might have used them if you're tracking your flight from Logan with Flight Radar 24. This is what they're using. Aircraft report their position in latitude and longitude, as well as their altitude, velocity, and other parameters. And our antenna currently has a range of 130 kilometers, so that's pretty good for our purposes. And this is really going to come in handy for when we're processing our data, and this will be a great way to kill anything that we might have thought was strange. It's okay, there was said to be a plane or a helicopter there. That's kind of what we saw, so we can filter that out and make sure we're classifying it and put it in that bin accordingly. Just to touch on our data processing and data flow, this is Eric Masson, he's over there. His mastermind, not mine. But so we have a dual computing strategy. This involves both edge computing and cloud computing. Edge happens at the edge. This is going to be at all of our sites using all of our instruments and acquiring that data and managing it. And then the cloud computing is going to be more for data archiving, post-processing, and applying machine learning algorithms. So this kind of gives a sense on how our cameras are talking to each other. So the things in red are happening simultaneously and executed in real time. So we have the edge computer that manages all of our video streams from those boson cameras from the Dalek, and those are saved to the disk, and detections that our visual algorithms are making using the YOLO model are going to be also saved to the disk and then broadcasted to our active tracking stations, which is the PTZ camera that we showed earlier. So once that is analyzed, we can say, okay, here's where we'd like you to point. PTZ points there. We get some high-res imagery. Then we are going to perform some additional data analysis with our other instruments. So like I alluded to, our radar, audio, ADS-B, et cetera. And this is going to supplement how we're approaching the data analysis. So here on the left is just an example of a time frequency spectrogram. This was taken over the summer on the CFA roof when an Airbus 319 jet flew overhead at an altitude of about 1.2 kilometers. You can see on the right here is the relative power in decibels. And the lighter color means a higher relative dB, which is a higher sound pressure. So you can see these signatures from planes. And if we train our AI algorithms to say, okay, this is what a plane should look like in terms of a time frequency spectrogram, then we can go ahead and filter that out as well. So, once our AI models are going to process tons and tons of data, I can't emphasize enough, then we'll determine if there are any outliers, which there may not be. And then if there are, we'll go ahead and review those manually. So just to touch on my progress briefly, I helped assemble all of the things that you kind of saw here, as well as the brains of each instrument, which are the electronic enclosures here. I wrote some data collection scripts for some instruments, and I reduced some system noise that we saw in the audio data. Tons of debugging, especially with USB cables. I installed some new hardware to increase our ADS-B range by over 50 kilometers, which was really exciting. And currently my work is focusing around time synchronization, so making sure our clocks are accurate and that our clocks are talking to each other and that they are precise and in sync with each other. And also moving from an iterative data collection approach to a more schedulized approach where we're saving files at the same time so they line up nicely. In the future, we're going to continue to do what we're doing, validating our sensors and our computing performances, and we're going to start transitioning into the phase 1.5, where we're going to create a copy of the system, swapping out some sensors and making some upgrades, and we'll deploy it this summer. That's all I have for you today. Thank you so much.
This is fantastic, Abby, an excellent presentation, and we are really grateful for your help. Just a few words. This observatory had to be designed from scratch. Astronomy projects never monitor things moving on the sky, and so we are grateful to Alex Delacroix. He joined us from the Palomar Observatory. He left Caltech and came here to help us in the design, so many of the things you saw were designed by Alex. And also Eric Masson is sitting somewhere over there, and he was responsible for the edge computing and lots of challenges with the data transfer because we have a huge data stream, and we are also looking at objects from above using Planet Labs data, and that's something that Laura Domini, who is somewhere here. Where is Laura? She's a postdoc. Right there, and she is now in the process of getting the first data and looking at things from above, not just from below. So that's exciting, and the fact that it's a new territory was signified by visits of 3 officials from the U.S. government in Washington D.C. Department of Defense came to my home to learn about what we are doing. Never happened to me before. And also a bunch of people who donated the funds for this project, several multi-billionaires that just came to the porch of my home. So there is a huge community out there that is very excited about the scientific approach taken here, and that is something that was not done before. And it's really exciting to have young people like Abby being involved and Laura. So we very much look forward to, and as Abby was pointing out, in a month or so we're going to Papua New Guinea. So if you don't see me back, there will be an open position, I guess. I will sleep on the deck next to the machine room, and we are going to collect any fragments, any particles left from the first interstellar meteor, which exploded there in 2014, almost 10 years ago. And you'll hear about the results if we find anything. Questions to Abby? Yes,
Sure.
Usually.
What are the faintest things you can see with the infrared camera? Can you get light curves of planets?
No, I don't think so. We're still trying to quantify that. I think right now we're really focusing on the let's see, this kind of approach. This is our MVP, or minimum viable product, for August, which is just to make sure our cameras are seeing something, so it's like a plane. And I think we're focusing on planes right now because, like I said, we have the ADS-B data to kind of direct where we are, and that gives us latitude and longitude. We can do that and point our PTZ camera accordingly there. But over time, we'll be able to see what the faintest thing is. We just haven't done tests to quantify that. But we had to do tests. So the Wellesley team is working on a lower cost system. They're also using boson cameras, but they're using a commercial grade camera while we're using industrial. So we did a side-by-side test with that to try to see what the faintest thing was. But that was limited by how tall our pole was with our target and how much sky we can get in the background. So I would say that's the closest test we've kind of done to quantify that, but I don't think we would see anything like planes. But you could see with the visible, like the Alcor camera, that's used to take beautiful pictures of the sky and a bunch of stars in the Milky Way.
Sorry, I meant planets, not planes.
Oh, planets.
Yes.
Yeah, well, I don't think we'd be able to see. Well, you could see planets in our solar system, but not anything farther than that, obviously. Yeah. Sure.
Before I ask a question, a little note on the same thing. My colleagues from Russia, they just bought one of those infrared thermal cameras, attached it to a 2.5 meter telescope, and now taking images in L and M band. So they were very excited. I think it was a student project or something like this. But anyway, my question is about the
The
airplanes.
difference is that it's a narrow field of view, whereas we
Yeah,
are looking
yeah,
at the
sure,
entire
sure,
sky.
sure. So I don't think you will see even Venus because it's too faint. My
Yeah.
question is about the airplanes actually, because the military planes typically have these ADS-B systems.
Yeah.
Transponder turned off. So
Right.
how will you distinguish between like a military airplane and an alien spacecraft visiting?
Yeah. So, I mean, I would say military spacecraft are probably doing maneuvers that aren't anomalous. So that's where we would probably look at the trajectories and such to determine, okay, this is probably human-made. But the cool thing about Flight Radar 24, and we also have access to a couple of other ADS-B databases like OpenSky, is that they actually get the information of military planes. So occasionally, if you're really bored, if you go on Flight Radar 24, you can click on an aircraft that's military, and it'll tell you some details, but not a lot. So that's coming in with MLAT, which is actually at a different frequency. That's the 978 sometimes. But for some reason, I don't know if it's because they have tons of receivers and they're just like triangulating or something, but they're able to detect the military aircraft. So we have a partnership with them that we are establishing so that we have access to their both real-time and historical data, so we can have those things that aren't saying, hello, here I am.
Most of the time we see birds.
Yeah, lots of birds.
Turkeys.
The great thing is this will be the first, whatever upper limit you get if you don't see anything is quantifiable and new. But I still wondered how you set the scope, the scale. How big a region did you need to look at to get something interesting as an upper limit?
Yeah, and I don't think we'll really necessarily know until we get a bunch of data and kind of see. But I think in terms of when we were coming up with our science traceability matrix and coming up with our parameters, I think that was definitely part of the discussion, and that also feeds into cost. You know, do we want to get things that are the best of the best, or do we want to kind of aim for an estimated value and accept those limitations as they are? So for instance, like our passive radar is going to get things, I think, a range of about 250 kilometers, whereas, you know, our ADS-B can only go 130 kilometers. So I think those trade-offs are really important to quantify now, and that's what we're really trying to do with each instrument and identifying what its limitations are and what its advantages are. And then that'll feed into our next phases and observatories over time. And then when we copy those systems and put them around in late stages, that'll give us more coverage. But that's a very good point that we're considering actively.
This system is about $250,000 in cost, and we have a budget for a few copies, but if we get tens of millions of dollars, which is really modest by all standards, then we will have enough statistics. Well, first of all, within a few years, more data than ever obtained by anyone on this subject, but we will get to the bottom of it based on the reports. In other words, we will have a huge statistics of all the objects in the sky. If we don't see anything unusual, forget about it, let's move on. That's the whole, because right now, when the scientific community didn't treat it, and the public is extremely interested in making all these ideas, it'll make progress in scientific knowledge. And if we can clean up the slate, basically say either there is something unusual or not, then we can move on. If we see something unusual, then it's becoming very interesting. Yeah.
Absolutely.
But that's the approach. The approach is to open our eyes and just treat it like a science program.
Yeah, see where the data
worry
leads.
is how much do you have to get to say...
Tens of observatories, tens of copies.
Tens of copies.
Based on the reports,
Yeah.
that will help us get to the bottom.
Okay, great.
Because those that reported, you know, based on the statistics, you can say that everything that was reported until now as unusual will be figured out if we have tens of observatories.
Sounds good.
Yeah. Yeah.
So let me make a comment here, which I haven't shared with anybody except Amir Siraj, who I suspect is not in the room, but probably knows well. And that is with DASH, our project, which is nearly finished until we had a computer crash on what used to be called Odyssey, now Canon, in 2021, which we've still not recovered from. But we have almost the entire Harvard plate collection digitized, images there, and what we can do, which I thought of, and Amir helped me think about, is look for at 100 years of full sky data for anomalous looking tracks. What might they be? Imagine if you see, and exposure times are typically 30 minutes, 50 minutes, some 90 minutes. If you see tracks that do not look astronomical, suppose you saw a sharp right angle or even a gentle curve, which may or may not be astronomical, but this provides a very long range view of what is going on full sky. So I think we can do this. It will require processing of the existing data, which is relatively simple, but we've never have written the code to look for things like this. So I invite anybody who wants to get involved and help rewrite code. We will get Dash back on the air to finish the processing, by the way, I hope within the next year. Just since I'm advertising all this, we have about 30,000 plates left out of the 550,000 plates right across the hall here. And the 30,000 left are some of the best plates of all, the large A plates. They're absolutely beautiful plates. And we save them to the end because we have to change the top end of the scanner to do it. But we demonstrated when we started that we can do it. But those will be particularly interesting. So one quick question to think about for comparing historical data with what Avi and company have started here, which is a wonderful current project. What are the relative sensitivities that are achieved in the optical? Obviously, the plate data is all optical. So in magnitude units and time duration units, that will be something to compare for how sensitive each survey is. Of course, the big advantage of the plates is it's 100 years of full sky data.
Well, one thing to keep in mind, the plates were collected from one observatory at a time, and what we are talking about is actually putting these in many locations. Also, the instruments nowadays are so much better in recording digital data than. And the other thing the issue I have with historic data and also eyewitness testimonies is that you can't go back and visit it and make sure that it's not an artifact. I mean, you will see something, you would not be able to repeat it. And here, if there is something unusual, we can repeat it and make sure. So, of course, it's of great interest. The government also has some data. They have a new office looking at past data. You know, people are obsessed with the past. I don't know, that's my attitude. I'm obsessed with the future. And it would be far better to use the latest state-of-the-art instruments rather than rely on something that existed 100 years ago. But we are happy to be involved in that analysis. At any event, what we are focusing on is getting new data so that we can repeat it. We have full control over the instruments, so we know what they were doing. Thank you so much, Avi.
Thank you.
All right. Hi, everyone. My name is Adam Wheeler. I'm a postdoc at Ohio State. I'm going to talk about stellar spectral synthesis, specifically this code that I wrote called Korg. And there's two things that I want to get across. One of them is the fact that if you're interested in model spectra of stars, you might want to try using Korg. Please try it. I think it works very well. The other thing that I want to do, actually, though, is to walk through, in a little bit of detail, the calculations that Korg is doing and that other codes that do the same job are doing, and highlight some of the places where systematic uncertainties enter the models, because there are actually a lot of them, and I think they're a little bit underappreciated. Okay, so to give a little bit of history, people started calculating sort of in detail model spectra of stars in the late 60s, early 70s. The two codes that I think of are Synthi and Moog, right? So Synthi was developed here by Bob Carews. There was another little flurry of activity in terms of development of codes to do these calculations in the 90s. Turbospectrum and spectroscopy made easy were both developed. All of the things that I've mentioned are still in use. All of them use Fortran routines written by Bob Caruso. So Korg is the first one of these things that's been written, as far as I'm aware, in about 30 years. So it's benefited a lot, I think, from modern computing, right? Computers have much more memory now, from more modern languages. And so I think it's a lot easier to use. It's much faster than other codes, so that's what's shown in this plot. Turbospectrum's pretty fast as well, but I have yet to try a set of inputs where Korg is not the fastest. So I wrote it for myself. I'm interested in the systematic uncertainties in these models. That's what I'm going to talk about next, but I think it also obviously could be very useful for a lot of people. Another advantage, it's written in Julia, so it's compatible with automatic differentiation libraries. If you want to know the derivative of a spectrum with respect to, say, an elemental abundance, that's what's shown in this plot on the left, you can compute that much faster than you could via finite differences, and that's on top of the speed difference that you already have. So this is a huge advantage if you're doing Hamiltonian Monte Carlo or gradient descent or something like that. Okay, it's well documented. I think it is the most well documented of any of these codes. This is something I'm quite proud of, actually. So that's why I'm showing you a screenshot of the documentation. Okay, that's the end of the pitch. Now I'm going to talk about what these codes do and where some of the systematic uncertainties enter. So the inputs to stellar spectral synthesis, like the big two that people think of, are the list of transitions, the line list, and the model atmosphere. So this is something that is computed by a code solving the hydrostatic equilibrium equations. So there's a list of transitions, and the model atmosphere is listing roughly as a function, what's the relationship between optical depth, temperature, and pressure. Maybe also it's telling you something about the depth into the atmosphere if you care about curvature, because red giants have puffy atmospheres where you have to take that into account. Those are the things that people sort of think of. There are lots of other things that are important. I've listed some of them here. I'll talk about some of them more in a minute. Let me take a little side note to talk about the structure of the atmosphere. So classically, people do this by solving the physical equations. And we know that doing 3D hydro simulations gives different answers than doing things in 1D. That's what's shown on the top here. This is from the Stagger project led by Zazerel Magic in 2013. And this is showing for a few different sets of stellar parameters the relationship between tau and temperature that you get through the atmosphere. And so I think it's the dashed ones are 3D, come from averaging 3D atmospheres, which actually produce convection naturally. And the solid lines are coming from 1D atmospheres, which are doing mixing length theory. Okay, so these things are different. It matters to the spectra. The full 3D hydro simulations are super expensive. We can't generate enough of them to just produce spectra with arbitrary parameters. But what I've been working on just for the last couple weeks since I've been here is actually using, so far, simulated observations, but using the fact that lines form at different depths to infer the relationship between T, tau, and pressure. Totally empirically without solving the equations, without necessarily, explicitly modeling exactly what is missing in the opacities or in the convection treatment or whatever, you can recover the change in temperature, particularly near the photosphere, right? That's where it's important. And we can actually recover that from data, which I think is really exciting. Okay, that was a side note. The first thing that any of these codes do is calculate how much of all the different species there are through the atmosphere, right? So you need to take hundreds of different things into account. This is where you would adjust for non-LTE effects. That's something that's currently not implemented in Korg, but I'd like to have that working very soon. Already here, unfortunately, aside from the NLT effects, which is its own fairly well-studied thing, there's already a place where systematic uncertainties enter. It turns out that for many molecules, the amount of energy you need to atomize them is not known as well as we would like. So this is an example that I stumbled upon totally by accident. This is a carbon-2 band synthesized by Korg and 3 other codes. And they disagree about what the absorption should look like, like the pretty significant level, like 50% of the absorption, 10% of the flux. And what's going on here is that the dissociation energy of carbon-2 is not known that well. If you use different dissociation energies, you get significantly different absorption. So this is, and you know, I happened upon this on accident. I have a collaborator with a student who's doing a more detailed survey of, you know, what are for all of the molecules, how significant is this effect? But it definitely matters, at least for these carbon 2 bands. Okay. Once you know how much of everything there is through the atmosphere, the main thing that any of these codes are really doing is adding up the opacities, or the absorption coefficients, right? So there's continuum absorption, that's what I'm just showing on this slide, and there's the contribution from individual transitions. Here I want to highlight a couple places where the models are not as good as we would like. The first one actually is neutral hydrogen photoionization. So it may surprise you to learn that these models have some issues. So in stellar atmospheres, you can treat most things as an ideal gas, and it works pretty well, but for hydrogen, you have to take some plasma effects into account. And so what Korg does, that's in blue, and what Turbospectrum does, that's in orange, right, they use this prescription developed for stellar interiors, the Michaelis-Humer-Dappin formalism. You know, it works well if you're only interested in the equation of state, but if you care about the monochromatic opacity, it's not as good as we would like. It leads to predictions in hydrogen lines that aren't quite right. And the details of how you implement it, right, you can see this here on the right and the difference between the orange and blue lines. Some of these details about how you extrapolate cross-sections beyond like the classically allowed energies, you know, these details matter, and it's not clear what the right choice is. Okay. The other big thing is that in the ultraviolet, metal opacities are incredibly uncertain. I think this is super underappreciated. So you can see all of these different lines are super different. This is what different spectral synthesis codes predict. All the stuff in the blue line, the Korg line, these are not atomic or molecular transitions. They're not transitions. They are autoionizing resonances in the photoionization cross-sections of metals. These are physically real. Their exact sort of positions and depths is not that well characterized, but what I have in Korg is it's the state of the art. It's from the top-based projects, you know, and I think it's important to include these because they are physically real. But you know, unfortunately, the models that compute them are very costly, and they're not perfect yet. So, for example, here I have to take these things and then adjust them. You know, take the energy levels and adjust them to the empirically measured energy levels from NIST. Okay, so be especially wary in the ultraviolet. Okay. There are also, of course, right, the other thing, maybe the main thing that these codes do is add up the contributions to the opacity from atomic transitions. The theory of this is like relatively good, I think. You can, each transition is described by, you know, a handful, depending on exactly how you parameterize things, a handful of parameters, 5 to 10 parameters. Unfortunately, all of them are generically uncertain. Even for some lines, the wavelengths are not known precisely enough to perfectly predict spectra. That's not really true for measured lines, but for predicted lines, which matter for getting, you know, total opacity right, the wavelengths are not super well known, and the rest of these quantities are in general not that well known. So you have to adjust them. You have to do astrophysical calibration. You look at a spectrum of the sun, maybe Arcturus or some other red giant, and you sort of twiddle with things until you get a good match. But I think that sort of process has historically not been done to sort of, let's say, like modern statistical standards. I mean, part of it is that it's really hard, but I think with current computational capabilities, it's doable. And this is something that Phil Cargile and Charlie Conroy here at CFA are working on. That's part of the reason I'm here. That's I think, a very exciting direction. Okay, so last thing, unfortunately, because the number of the resolution at which these things are computed, the resolution at which model atmospheres are computed is not that high, right? So they generally have sort of 50 to 100 layers. You can take that, you do the opacity calculations. When you then solve for the flux at the top of the star, you know, depending on numerical methods, there's actually about a 1% uncertainty. And this is not just comparing like high order to low order methods. These are methods that should really be giving, you know, it's not clear which one is more precise or more accurate. And it's just sort of an unfortunate fact about the resolution of the model. So this is something else that would be really nice to improve. Okay. Thank you.
the unknown atomic constants based on what we observe from astronomy, or will it always go in the other direction?
I think there's definitely a possibility. I mean, that's one of the things that I'm most excited about, actually. I think, yeah, I mean, yes, the answer is yes.
Eric, and then Matt.
So I was just looking at the view graphs, and you had one comparing the 3D turbulent model with the Microlensing theory. And my general impression was, wow, the Microlensing theory is really good. It matches up. And he said, no, that's no good. And then you had another graph where you were comparing the depths of absorption lines, that one that just went by,
Yeah.
KME and so on, and you said that's going to be 50% off, and then I just well, it looks like 10%. So the question is, if you make a new observatory or a new code or something, and you'd say, if I had this capability, I could answer some question. What's that question? And Avi suggested one, but why are you doing this? How does this?
Yeah.
How do these differences really help?
Yeah. So I mean, just to clarify, what I meant here was that like the absorption according to Korg is twice as deep as the absorption according to turbulent spectrum. So that's the 50% that I meant. But yeah. Why am I doing this? I care about chemical abundances. I'm interested in nucleosynthesis and galactic chemical evolution, and all of these things that I just mentioned are holding back the precision of chemical abundances of stars. So if you different big spectroscopic surveys like Apogee and Galileo, for example, if you look, these measure sort of 20 to 30 abundances per star, and if you compare what they say, they do not agree. I mean, the disagreement is way larger than the observational error, or even, I think, what most people are aware, in terms of the systematic error.
And that would be due to the interpretation by these various codes.
Yeah, things like this. I mean, there are more things even than I mentioned, NLTE and 3D effect, but yeah.
Matt, go ahead.
Yeah, I'm curious about what has made your code so much faster. Is it autodiff or something else?
It's not autodiff, because autodiff is almost not used within the code. I think it is very helpful to be able to use modern amounts of RAM. So I don't, Korg takes something like 600 megabytes, right? Which is it's kind of a lot. 50 years ago it was an insane amount, but it's not a problem today. I think the other thing is just that I prioritized making it fast. I've spent a lot of time doing that.
Thank you so much, Adam. We need to move on.
Go. Okay, so I'm going to tell you a really fun story about a star that we believe swallowed its planet. And this is work that has been done with a ton of people. And that's really one of the joys of doing this project. The lead of this paper was Kisha Lede, who's right over here. And he led the observations, and then we did a lot of work interpreting this source. And I think one of the many things that this has taught me is that it's important not to take yourself too seriously. We're talking about a star swallowing a planet, and so to that end, when you have new data, it's important to make new theoretical models. And so that's what I've been busy doing in my office. If you ever wonder what I do when I'm sitting there, I went to Sarah's and I got bugles because apparently I'm 6, and I've been eating them. So we're looking at the story of a star that swallows its planet. Let's start with the data. So this is the light curve. What we saw is a brightening in optical wavelengths. This is data from ZTF. And then this was supplemented by a really incredible light curve from WISE, where we see the infrared. And what happens is that this source starts brightening in the infrared even before we detect it in the optical. Then it has a really rapid, about 10-day optical brightening, and then ever so slowly it fades away both in the visible and in the infrared. The spectral energy distribution really changes over that time too. So we, at this time when we have optical emission, there is sort of this optical bump in the light curve, but there's already an incredible infrared excess. And then over time, the spectrum becomes more and more infrared dominated. And from that, we can make some estimates of the amount of material that's surrounding this star, and we estimate that it's something like 10 to the minus 6 solar masses of dust are needed to make this. This star is in the galaxy, so it's also behind a lot of dust on the line of sight. So that will be part of the story later. So that's what we saw. Why do we think that this is a star engulfing its planet? And today I'm going to talk just a tiny bit about those data and a lot more about the sort of things that we hope to learn from that. So the announcement and discovery paper, I think, very correctly focuses almost exclusively on the data and only a little bit on the interpretation of this event. And so I thought what I could add to that is a little bit of discussion of this in context. First of all, that kind of story of a precursor brightening, some outburst that starts fast and then fades away and becomes redder, and eventually forms a lot of dust and becomes infrared luminous, is exactly what we see in merging pairs of stars. And so if a merging pair of stars is a really dramatic disturbance to a star's existence, you can imagine the opposite of that is if a meteorite or a grain of sand falls into a star. It's no big deal, right? And so somewhere in between is the planets. And one question is, how big of a planet do you need to cause this sort of disturbance? So by association to what we'd seen in stellar merger transients, we originally thought this source was a new addition to that class. But over time, we started noticing that it was scaled way down in every way, in luminosity, in ejected mass. And that's part of the story that I'll tell you. So stars swallow their planets because they change in size. And in particular, the sun is its current radius, but as it evolves, and as you know, it gets bigger and bigger and bigger. And that means that, for example, many of the exoplanets that we know, not from direct imaging, but from the transit method and RV surveys, will all be swallowed eventually. So we've known for a long time that this is a process that should happen. We see planets that are close to their stars. In particular, the hot Jupiter population was really just surprising when it was first discovered. And we've seen planets tidally decaying towards their stars. We see red giants that are spinning anomalously fast or have strange abundance patterns. And trying to quantify that before and after with this process in action was really the goal here. Okay, so what happens when a star swallows its planet? First, I want to talk about two aspects. The first is that when the planet falls in, that's not a completely gentle process, and there's some ejecta associated with that phase. And the outermost skin of those ejecta become a transient event that we can see. And the second is that the planet's orbit actually decays as it falls into the star. So in terms of transients, what we've seen in merging pairs of stars is that those ejecta and their cooling power transients that we can see. So material is shock heated, it's expelled from the system as it expands and cools. It doesn't necessarily have a heat source like radioactive decay in a supernova, but just that expansion, cooling, and becoming optically thin creates a light curve where the luminosity rises and then fades in time. This is a lot like often recombination of hydrogen modulates where the photosphere is because it changes the opacity so dramatically. So these end up looking like scaled down type 2p supernovae. And they're powered, of course, by material that flows out from the system. So as the pair comes together to conserve angular momentum and energy, some material has to be thrown out. So a little bit of material is given in a relative sense, a lot of energy and momentum, and it flows out from the system. It runs into itself. Those internal shocks inform its internal energy. And this is a process that starts slow but ramps up really dramatically, so that by the end phases, you started with a pair that's orbited for maybe billions of years in the case of a low-mass star, and it merges in a timescale of just a few orbits at the very end. So that's what sets this transition from a precursor to a transient. Because one thing you might be wondering is, how do you take a system that was orbiting for some huge amount of time and create a transient that is on a human timescale out of it? And we think it's the tail end of that exponential runaway of mass ejection and orbital decay that are coupled to each other. From simulating pairs of stars, but sort of pushing down in mass, we see that the expelled mass is just linearly proportional to the mass of that smaller object, the secondary. And that comes directly from thinking either about energy conservation or angular momentum conservation also. But it's kind of confirmed by simulating these things. And so if you extrapolate that, we look at the population of, these are the known transients that have been associated with a possible stellar merger origin. They have an interesting relationship between luminosity and timescale. That actually maps, we think, to properties about their velocity in the pink contours, the ejected mass. So the more luminous events probably have higher ejection velocities, but also higher ejected masses. And way down here is this new event. So this is one of the best studied events, this V1309 Scorpius. It's a transient in our galaxy where we saw a 10 magnitude brightening and then a fade away. When people looked back in time in the OGO microlensing survey, they saw this source as an eclipsing binary with a decreasing orbital period. And so we know really well that this was about a 1.4 solar mass star merging with a 0.1 solar mass companion. It turns out that the host star, to the best of our knowledge in this system, is similar to V1309 Scorpius, and yet it's like 1, 2, 3 orders of magnitude fainter and has less radiated energy. We think less ejected mass by that same linear scaling. So clearly, the total energetics of this are way down. And to the extent to which we think that's proportional to the companion mass, these very low luminosity events, we think, trace substellar, maybe planetary companions. Okay, so the planet has skimmed across the surface of the star, ejected some material which drives a transient we see. What happens next? And like a satellite that's coming into the atmosphere, it feels a drag force. I was just at over the April break, I was at the Smithsonian Air and Space Museum, and I saw the Apollo capsule where you see the bottom is totally ablated by the heat that it experienced going through the atmosphere. The planet experiences the same thing. So it interacts with a column of gas. It's heated up. It feels a drag force. In addition to heating up and eventually destroying the planet as it falls in, it's a heat source for the star. And so we can ask whether or not the star feels that effect, and if that power that's added is tiny compared to the stellar power output, then the star won't even notice. Its structure isn't perturbed. We as observers probably wouldn't see a 1% blip in a star's brightness necessarily. But on the opposite limit, if two stars merge together, this is a really dramatic disturbance. So where does that transition lie? It turns out it has, for giant planets, say like a Jovian planet, it's somewhere around the hot Jupiter to warm Jupiter transition. So we think that we saw this transient in part because it was a very close-in Jupiter mass planet. And as a result, it disturbed its star enough that it caused this brightening and then fade away. But more distant giant planets, or heaven forbid, the terrestrial rocky planets, when they're swallowed, they put in such a small power output that the star doesn't even really notice. So that's something kind of humbling to reflect on. Okay, well, I will. Okay. So people have been thinking about this and anticipating this for a while. So we have some really interesting simulations here. This is a smooth particle hydrodynamic simulation. And now we're looking at a slice. And what we'll see is that this Jupiter-sized planet actually falls in quite a ways in just a few orbits. And so what's happening is it's experiencing the ram pressure of passing through this stellar material. It's being slowed down, but it's also being ablated. So its mass is almost decreasing linearly with radius in this simulation. And at the very end, it's been essentially halted by that drag force. And the remaining material is lower entropy than its surrounding. It's heavier, and it just sort of buoyantly falls. So we can start to analyze this sort of simulation to understand what is the nature of that energy injection into the stellar envelope, where is the planetary material deposited, so like would we see it in surface spectra, that sort of thing. Okay, I want to finish just by looking a little bit at some of the bolometric sort of physical properties that we infer from the light curve of this event. And in the background, Kishale overplotted the population of stellar merger transients. And there's a couple of really interesting differences. So one is that this is just a lot less dramatic. So the photosphere didn't expand by a factor of 100 like we see in some stellar mergers. There's less ejecta mass. That's in this lowest panel. It stays comparatively warmer on the photosphere. And that's again tracing the lower ejecta mass. So the ejecta become optically thin sooner as they're expelled because they're so low mass. And then second, instead of a big brightening and then a starting to fade, we just see kind of a power law decline. And we think that this is the star starting to return back to normal, basically. So this is a function of how deep the heat is deposited inside the star. It takes like a local Kelvin-Helmholtz time to reach the surface and start to diffuse out. And so really, over time, as we continue to follow a source like this, we're tracing the deposition of heat within the stellar envelope. So finally, I just wanted to highlight that, this is a huge collaboration. So it's been both a joy to get to talk about this really fun science, but also to work on it, because I think working on it was really a Venn diagram of a number of facilities. We sort of pieced together that because of the number of different telescopes that were absorbing this source, but also people and bringing together a bunch of different expertise. So thanks so much.
While we're answering questions, can you show the elephant that you skipped over? The elephant in the room.
The elephant in the room, exactly. Where did it go? I skipped it again. So the elephant, okay, so let's imagine a conveyor belt. Maybe there's sushi on this conveyor belt. If you had one more piece of sushi, it's no big deal, but if you sit an elephant on the conveyor belt is the stellar power coming out from the core. It takes 10 to the 5 years for the heat to diffuse out from the center of the star. If you add something way bigger than that continuous output, that's a big problem. So this is a question of whether the energy deposited by the mechanical decay of the planet is, compatible with the flux that's already going out, or whether it's much more. So this extremely cute elephant would be a big problem for our conveyor belt. Just like a giant planet is a big problem for a star.
Thank you. Questions, please?
Yeah, so now that we know, or you guys know, what these things look like, how many do you expect many more of these to be found in transient surveys? Can we make some trigger go up if we see others?
Do you want to go ahead?
Sure. Right, so that's the hope. I think one of the key signatures that, in my mind, I see is that these behave very differently in the infrared and optical. And infrared data, as you know, is something that's been historically very hard to get. But as of this time, even as we get into this infrared survey era, we are mining archival data from WISE, looking for things that have infrared brightenings and also different looking optical brightenings that might be a signature. But very soon, as these infrared surveys come online, we'll be able to use optical surveys to find these initial outbursts and then look for this lingering infrared emission that stays on as ways to identify these things.
Kishila, if you believe what Morgan was saying, I'm not asking you to believe it, but if you do, then it has to be a result of the evolution of the star. So then you might pick stars that are at a particular phase in their evolution so that they engulf the planets. Does that pick up a very narrow range of stars, or is it, yeah?
Right, I think the most dramatic transients would come from these hot Jupiters, and that rate is like 1% of stars. So I think, if that's what I think
But you need the star to evolve and engulf them.
Yes,
right.
yes. But so if it was like a Jupiter in our own solar system, we wouldn't have, I don't think we would be able to identify that because that energy is so small compared to the red giant's luminosity at that stage. But I think the ones that will be easiest to identify, which is like the one here, are the things that are just evolving off the main sequence and are running into this big Jupiter. Right.
That's the assertion, at least. And I think one of the goals is to test this. And yeah, to your point about searching for these, something that I've learned from you is that it's really easy to find variable sources in the night sky, and it's really hard to prove to yourself that you know what they are. And the multi-wavelength capability has been kind of key to the fingerprint of just totally cooling gas, basically. There's no extra heat source in this system.
Another thing to keep in mind is some white dwarfs show planets next to them, and that was shortly after the red giant phase, and there is this puzzle as to why do they have planets next to them, whether they survive the expansion or not.
I know, it's really an amazing puzzle, but we don't know.
Eric and then
could that be the explanation for tiny star, and you replace your hot Jupiter with a super Earth?
Well, I mean, the short answer is we don't know, and yeah, I mean, I think there are other objects that could broadly be compatible with this sort of process, but we don't have a sense yet of the full range of possibilities of what it could look like. And in particular, it does seem some mass ejection and dust formation is part of the story, but how that affects the stellar luminosity, etc., is probably matters in detail.
Can you confirm whether the star is actually like a subgiant, whether it's just leaving the main sequence?
Yeah, so the reddening and distance have some degeneracy and uncertainty. It is behind quite a column of dust, and so it seems consistent with a star that's sort of, the data are most consistent with something just off the main sequence, but it's, maybe 1 solar mass and 1 to 4 stellar radii. So it could be still on the main sequence.
Okay, maybe the thing to do is take Adam's latest version of the code and get the spectral spectrum when compared to
Yeah.
Please.
I just had a quick question about the mass ejected versus the mass ratio. That plot that you showed, could you bring it up? I couldn't read it that quickly, so I wanted to ask, there were these data points. Are these simulations that you
Yeah.
and then compared them to the, so that means the code is producing the dynamics you expect really well?
Well, I mean, to be fair, we ran a bunch of simulations and then we figured out what we expected after we saw the simulations. In essence, we learned that the explanation for what the simulations were showing was really simple, and it's just essentially the conservation of angular momentum as these things go from the start of mass transfer to sort of merging together. And so to tighten the orbit by a certain amount, you have to take a certain chunk of mass and throw it out to infinity. And if you calculate what that mass is, then you can get these estimates. And the exact normalization comes from the specific angular momentum that you give to that material. And so that's a coefficient that you measure from the simulation.
I guess I was wondering if this depends on the viscosity modeling at all, understanding viscosity here.
In this case, it's probably just gravity. But like in certain limits, the thermodynamics would matter. Probably not the viscosity, but the thermodynamics.
Okay, I just wanted to ask everyone that is interested in the event we're having after, just stay around. We will have it here, and let's thank Morgan for one.
Thank you all.